Hello again. We're going to continue with addition reactions to alkenes. We are going to start with hydro, what's it called? Halogenation, and then go to hydrogenation. I don't know, it's July 4th, and I'm still working, so you're just going to have to bear with me for the moment. All right, so I'm going to share my screen. Okay, so halogenation is the addition of a halogen. And the halogens that we're going to really focus on are going to be chlorine and bromine. And the good news is these are symmetrical reagents. Right? I either have Br, or I have Cl. And I'll put in all my lone pair because I like to in my Lewis structures. Now notice the halogen splits up and one halogen atom gets attached to each carbon of the double bonds. Now the nice thing about this is there is no regiochemistry. I don't have to worry about Markovnikov's rule because one carbon of the carbon-carbon double bond gets an X and the second carbon of the carbon-carbon bond gets an X. Because they're both X's, there is no regiochemistry. It does not matter what carbon I'm going to start with or end with because I just get the addition of the same atom to both of those carbons. Now the interesting thing about this is that this can be used as a qualitative test, right? This can be a qualitative analysis test for testing for multiple bonds and unsaturation. So this is called a bromine test. If I take a little bit of bromine water and I'm adding it to a sample of an unknown compound, now bromine is sort of an orangey yellow, and that gives a definitive color to the solution. So if that color disappears, right, if that color disappears, that means that bromine is reacting. If there's a double bond or a multiple bond, this could happen with triple bonds as well. The fact that this bromine is reacting with something, right, that indicates the presence of a multiple bond. Because now the bromine is reacting, the bromine is adding across the double bond and forming a colorless dibromide compound. If the color persists, that means that bromine is still there, right? So if the color stays and never leaves, as soon as I add the bromine, it's not reacting, which means there is no multiple bond. So this is actually kind of a cool little test that you can do for alkenes and alkynes. So the way I do this is that I can either carry this out with pure reagents. Mostly I don't do that. I'm going to use an inert solvent such as CH2Cl2. This is called methylene chloride, or it's also called dichloromethane. And that's a very, very, very common solvent that's used in organic chemistry. So notice I have here bromine attached to each other. Remember, bromine is a diatomic molecular element. So one of the bromines adds to one carbon, the other bromine adds to the other. What I'm forming are these new bonds, and I end up with a dibromoalkane. So again, this is less complicated because it's a symmetrical reagent, and I don't have to worry about which carbon my bromine is adding to because it adds to both. There is one thing I do have to tell you though. My addition is going to be stereoselective. All right, so there's no regiochemistry, but there is stereochemistry. So a stereoselective reaction is a reaction in which one stereoisomer is formed or destroyed in preference to all others that might be formed or destroyed. When I add to a cycloalkene, for example, I only get the trans product. And that correlates to something called anti-stereochemistry. Oh, this is an interesting little thing. This is the bromine test. So this would be a negative result, and this would be a positive result. I should probably pay attention to my slides next time and fix some of these goofy little errors that I make. What that means, I didn't write it on the next slide. So if I have a stereo or I have an alkene, what I'm going to get with the reaction of bromine is the trans. So I'm going to get one bromine up and one bromine down. So this trans product is the one that forms. I do not get the cis where they're both up or down. So this does not form. This correlates to anti-stereoselectivity because they're on opposite sides, so that's anti. Syn would be this guy. So this would be syn, and this is anti. This syn doesn't form, I have the anti-stereoselectivity. And for our purposes, we have to start with a cycloalkene in order to see that difference. Now, why does that happen? Well, it happens because of the mechanism. The first step is the reaction of a nucleophile and an electrophile to form a new covalent bond. So my pi bond, which is nucleophilic, remember, this is electron rich, is going to react with my bromine, which is actually an electrophile, which is a little hard to explain at this level, but this comes out and it breaks the bromine-bromine bond. And then what happens is I have this weird bromine intermediate. I have a positive charge and this comes in right away and I get this species which is called a bromonium ion. So that bromonium ion is what is my intermediate in this reaction. This happens really, really fast. So my carbon-carbon bond doesn't have time to rotate. So this bromine comes in right away, and this is actually going to be the intermediate in this reaction. So remember, this is called a bromonium ion. If it was a chlorine that did this, it goes by the same mechanism, that would be called a chloronium ion. So in step 2, I have the reaction of a nucleophile and an electrophile to form a new covalent bond. This is this bromonium ion is electron poor. Remember, it's got a positive charge. This is a nucleophile. This is electron rich. So these electrons are going to come in and kick out this bromine. But look at what happens. The top face of this sort of cycle, this whole top face is not accessible. My bromine can't come on the same side as the bromine that's there. It has to come in from the opposite face. So it has to come in from below, right? So what that gives me then is this anti-relationship, because I get this anti-periplanar or coplanar orientation of those bromine atoms. So if I look at this in terms of a Newman, this is going to be my anti-staggered Newman conformation, and that's what results. So I have one bromine that goes down, and I have one bromine that's pointing up. That is my anti-stereochemistry. I'm really only going to see that if I have a cycloalkane. So when I do this with a cyclic structure, right, if I add chlorine, which is Cl2, or bromine, which is my Br2, and I'm adding it to a cycloalkane. So it doesn't have to be cyclohexane, it can be a cyclopentane or pentene, it could be a cycloheptene. What I'm going to get is a trans diaxial product. Only the axial positions adopt this necessary anti-coplanar orientation. So the initial trans diaxial product, which is a conformation, right, is in the more stable trans diequatorial. So this is what you end up with, right? This is going to be the conformation. This is going to be the preferred conformation. But it has to start out there because I have to have this anti-relationship. I form this bromonium ion, and the bromine has to come in from the bottom. Those two bromine atoms have to end up in this trans diaxial conformation. Okay, now we're going to segue a little bit. Let's look at what happens when I have a carbocation and it actually can rearrange. Carbocations can do three things. They can form a bond with a nucleophile, they can rearrange, or they can eliminate. And we're going to see that in a little bit in terms of the elimination. So we're kind of backtracking now. We're going back to hydrohalogenation and to hydration. So as we've seen, the product of my electrophilic addition to this alkene, forgot to turn that on, involves the rupture of a pi bond and formation of two new sigma bonds. Now, in the following addition, only 17% of the expected rearrangement is formed. Now, why is that? Or of the expected product. So I should get hydrogen adding here and chlorine adding there, which would correspond to this product, right? This would be my typical Markovnikov addition. But I don't get that. I only get a little bit of this. What I get as my major product in 83% is this structure where my carbon skeleton has been rearranged. My RAR always means rearrangement. So how does this happen? Well, either an alkyl group or a hydrogen atom will migrate with its bonding electrons from one atom to another. And what I have is called a 1-2 shift. So let's think about this. Here, if I go through the Markovnikov type situation, I should get this secondary carbocation as my preferred product. Remember, if I add to this carbon, I'm going to get the primary, if I add the chlorine to that carbon, I'm going to have to go through the primary carbocation. This is the carbocation that would result through Markovnikov addition. But notice this carbon is now this carbon, which happens to be this carbon. So the chlorine doesn't actually end up on that carbon. The chlorine is going to end up on this carbon. And what happens is one of these methyl groups actually shifts over to form a new carbocation. And that new carbocation is going to be tertiary instead of secondary. It still has a hydrogen on it. And this is tertiary, this is secondary, this is much more stable. And now you can see my chlorine comes in and adds to get to that carbon to give this product. So this is a common occurrence. Let's look at how this happens. So the first step is to add a proton. And what I'm going to form is the carbocation, right? This is my normal step. I'm going to pay attention to Markovnikov rule. This only has one hydrogen. This carbon has two hydrogens. So my carbon's going to end up, or my hydrogen's going to end up there, which gives me, I'm going to draw in that hydrogen, this secondary carbocation intermediate and chloride minus. That's the normal route that these reactions will take. What I'm going to get now, though, is I have the rearrangement of a bond. One of my methyl groups actually migrates. And this migrating group can either be a methyl group, an alkyl group, or a hydrogen. It takes its bonding electrons with it. And the driving force is to form a more stable carbocation. So this whole methyl group migrates. Remember, this has that hydrogen on it. And what I get is now this methyl group is over there. And my positive center just shifted to that carbon. So the driving force is the formation of a more stable carbocation. Because remember, tertiary is much more stable than secondary. So there's a really large energy benefit in order for this reaction to occur. Now, my third step is what you would expect, where I take my nucleophilic chloride and then my electrophilic carbocation, and I form a new bond. So this bond is the new bond that I'm forming with that. So I have to look for these rearrangements because carbocations commonly rearrange. In fact, if they can form a more stable carbocation, they will. So this is a trick that you have to learn when you're predicting products and drawing mechanisms, is if you get a carbocation is this carbocation one that can rearrange? Or is this carbocation the more stable form and I can't form anything more stable and it reacts as is? So here's a question that you might get on a test. Propose a mechanism for the following transformation. So what I'm going to do is figure out where my hydrogen is going to go, right? Because this is going to react with bromine, right? This is the carbon that has the more hydrogen, so the hydrogen is going to go there. So I'm going to draw that arrow pushing mechanism. And what I notice now is that when I do this, I get this secondary carbocation. Notice I have a 5-membered ring here. And this is the carbon that's next to the methyl. So here's my methyl and here's this carbon. So what happens is this entire group is going to shift. And what I'm going to get is a 1,2 alkyl migration. And I'm going to end up with this carbocation. And now my bromine is just going to form the new bond to get to that product. I'm going to do the same thing with this one. Here I have my 2 hydrogens. This hydrogen in the water, right? First, I have to protonate. So what I have is this oxonium ion. These electrons are going to come out. What I'm going to get is this spirocyclic system. And what I'm going to end up with is this secondary, this is actually a tertiary carbocation. But what's going to happen is this bond is going to migrate. And it's going to migrate because now I have this 6,5 system. And what I'm going to end up with is the positive charge here. Right, so this is the carbon that ends up there. Now, water is going to come in here. And then I'm going to end up with the oxonium ion. Which has the O, H, and H. And then I'm going to have another water come in and get rid of the hydrogen. And that's how I get that neutral alcohol. So hopefully this makes sense because you really have to know these carbocation rearrangements. So let's summarize carbocations. The carbon bearing a positive charge is sp2, hybridized. It has bond angles of 100 degrees. And I have this stability. And this is more like, tertiary is really, really more stable than secondary. They're stabilized by the electron withdrawing eductive effect of that positively charged carbon. Methyl and primary carbocations are so unstable that they actually never form in solution. And carbocations may undergo rearrangement by a 1,2 hydrogen or methyl shift when the rearranged carbocation is more stable than the original carbocation. The most commonly observed pattern is from a secondary to a tertiary. When I think about carbocations, they undergo 3 types of reactions. They can rearrange, they can add a nucleophile to form a new covalent bond, Or, and this is the one that we're going to talk about a lot in the next chapter, they can lose a proton to give an alkene, which is called elimination. I will tell you that you will have to identify rearrangements on your test and your quiz, and you will have to be able to predict the products and draw the mechanism of various rearrangements as we go through the rest of this chapter. That's one of the skills that you're going to need to remember. And at that point, I'm going to stop and I will be back. Okay, see you in a bit.